Let's do LED week. Let's see. Kate, can I share? Oh, I can. Okay, great. So we'll do the share and then we'll present. Let me pull up the chat so that I have it in view. Okay, cool. So it is LED week, which is an exciting week for makers. LEDs are the core of how most of the things that we make glow will work. And so we're just going to do a deep dive into this one topic. It's a place to point all of that Arduino skill that we've been working on so that you can have things glow in the way that you want, that you can sort of play around with electronics, get started with that, and to use some of those code skills that we've started. It's also nice because there's not a lot of trickiness to it. I mean, there's a few tricks, but we're going to sort those out this week or in the next hour. And then hopefully it's something that you can really go after. And then this is a 2-week intro to electronics, where really we're sort of opening the door to where we'll go deeper later. So LEDs are the best start to that, I think. And then next week will be sort of canned projects, things that you'd find on Adafruit or Instructables, and we'll sort of work through that way. But this week we're going to stay focused just on the Blinky things. And so our goal is to stick to these. So here's our topics. We're going to talk about LEDs as diodes because that's an acronym in the name. Then we're going to talk about LEDs in Arduino circuits. Then we'll go over the core of what pulse width modulation is and like how you can get lights to fade, which is something that is quickly done in Arduino with analog right, but it's kind of magical what's going on behind the scenes. We'll do RGB LED theory. And when I've taught RGB LEDs in a high school, it's a really good one to just gutturally yell all of those letters in a row. RGB LED. It's fun. Gets high schoolers amped up. And then there's some simple animation techniques we're going to go over. We'll talk about how can you manage more than a handful of LEDs? How do you deal with a lot of them? And then how do you do complicated animations? And then we'll sort of dip our toe into circuit permanence. And for any of you who are in the space over the past week or so, I handed you probably a little gift baggie of electronics things. And so we'll see how that fits on the spectrum for what's going on. So we're going to talk about lots of things. But my general attitude about this particular week of stuff is that people love Blinky projects. They're a great place to start. They're a good place to build out skill. And let's see, here's the Adafruit link for Blinky projects. So look at this like fun collection of animated GIFs with all these different sorts of projects that are essentially just LED based projects. Some of them are LED and a few other things. Some of them are basically just LEDs. And they're all sorts of different options that you can have and play around with. So these would all be things that are hopefully like on the menu after this week. And the nice part about Adafruit is that these are full instructional tutorials where like, if you want to make this T3 time triangle thing, you can click on it and here are a list of instructions, provided they're not out of stock. But like, here's a write-up, the physics model, the documentation. We're going to sort of like get going in this direction where there's LED understanding and then LED projects and sort of get you pointed towards where directions like this are going to be in your wheelhouse. So that's what we're going to do. And I think people in general, they love Blinky lights. They're just great. They're mesmerizing. We all like watching them. It's just a human. It may be like because we like fire for a long time. We liked watching, staring at a campfire. Maybe it's the same sort of thing, just like, you know, in the 2000s. So LEDs in general are a fascinating thing. They're light emitting diodes. So that's the 3-letter acronym. And basically they're just a special subcategory of a diode. And a diode is a piece of electronics that lets electricity flow, but only in one direction. And so LEDs have a positive and a negative side. There's lots of charts and graphs to try and understand the exact nuance of how they work, and we won't need to know that. But they glow as just sort of a byproduct. It was almost an accidental discovery that we could make LEDs when the intent was to try and figure out how to make electricity go in just one direction. And so that's kind of fun. And then diodes, LEDs, and solar cells, like solar panels, are all sort of in the same family of things where light and electricity come together. Specifically for LEDs, you got these interesting things where they use up some of their energy to make that light and to make a one directional junction. So those are all things to take into account. But let's see, if we're headed back to here, this is a link to a video where you can see a little bit more about how those are related. And what's useful here is to take a look at this particular graph, and we're not going to decode what all of it means. But there's this point where if you have enough voltage applied to an LED, all of a sudden the current will start to pass through it, but only in one direction. If you have a voltage build up in the other direction, up to some point where it'll break, up to some point, it will stop the current from going backwards. And so that's the point of a diode. An LED is just one of those that glows when current goes in the right direction. So LEDs come in all shapes and sizes. There's tons of things to know about them, but one of them that's really important is that a good data sheet or a good LED comes with a good data sheet. And so that gives you everything that you might need to know. And so here I've got a link for a data sheet. This is a Cree LED, and Cree, I think, is a brand that's sold at Home Depot. Actually, they make anything down from these little light bulbs or little LEDs all the way up to LED light bulbs. So they've got all sorts of stuff. A data sheet has tons of information. This one's 14 pages long, which is pretty long for an LED data sheet. And it's got all sorts of stats and figures. Most of these, I absolutely promise you, you're not going to need for maker projects. If you're buying these in bulk, like you're buying 10,000 of them, then you should evaluate a lot of this. But for us, we're just going to need to know a few key stats. So it's worth it for us to go back and take a look at those key stats. We've got our power dissipation right here. We've got our forward voltage, our forward current, and those are the three things that you should look for. The forward voltage drop is how much energy the LED uses just to be on. It says in the depletion zone, but that's just like a part of how the LED works that we don't really need to know. The forward current is an important detail. That is how much current your LED can pass safely in a stable way. And there's definitely like a stable range and a for short bursts of time kind of range. And the power limit is really how much power can it get rid of as a function of joules per second. So this is like a maximum limit for how much brightness could you crank out of that LED? How much energy could it dissipate safely without dying? And we're going to see a little bit later. I have a video queued up where we can watch an LED get burnt by having too much voltage and current applied. But a data sheet like this can be kind of a bear to read. You won't need to read them, but it's good to look for these three things. And sometimes they just have the symbol that go with them: PD, VF, and IF. And so PD is power dissipation, and those are usually in milliwatts. Forward voltage is the voltage drop. And if you've pulled an LED out of the kit on the foundation shelf in the back of MakeHaven, they're like conveniently listed with the forward voltage drop of each one of the colors of LEDs. This is the voltage that the LED itself consumes from the circuit. And we'll see that in a minute. And then there's the forward current, which is the average running range that you want to keep your LED in. So that if you want to keep it stable and running for 10,000 hours, which is sort of the average expected lifetime of an LED, you want to stay in that 10 to 30 milliamp range for one of these LEDs. And that's pretty normal for like a hobby 5mm LED. Oops. And so how do you deal with this? Like, how do you bring these things together for LEDs with Arduino or any of the platforms? So the ideas that we're going to cover here are specifically targeted at Arduino, but if you wanted to do LED with Raspberry Pi or with other platforms, you totally can. And these same ideas are going to work pretty well. So if you want to have an LED, there's a few ways that you can implement them. But the simplest one is to just sort of hook it up to power, right? And so if you want to hook up an LED to power, an LED is denoted by this symbol right here. So it's the little arrow pointed at a wall, which is kind of like saying it's one direction of current flow and it's pointing in the direction of current flow, and then two little arrows. Those two little arrows represent light coming off of the LED. There's photo transistors which have the arrows pointed the other way, but these are LEDs, so they come off. This is the simplest way to hook one up, where you've got your 5-volt supply and then current comes down through. I have this little marker coming down through to show that current comes down through the resistor, through the LED, and then out the bottom. If you're trying to implement an LED, you always want to pair it with a resistor, because LEDs, it turns out, are semiconductors and they don't actually follow Ohm's law, which is kind of fun. They're a non-ohmic device. But resistors totally are ohmic devices. They follow Ohm's law. And so you can use a resistor to quickly, easily, and cheaply set an LED up so that it's going to have that optimal current flow and that it won't hurt itself by passing too much current. Because this graph that I've got tucked in the top right really shows, I think, that, well, it's a very steep blue line. LEDs are either off or they're on. And without the resistor there, they can definitely hurt themselves. So having just an LED partnered with a resistor is totally fine. I've got both of these configurations on here with the resistor on top and the LED on the bottom. And both of these totally work. It doesn't matter which order the resistor and LED are in. They can be either one first, and it totally works. Oh, good question. They don't follow Ohm's law. I've taught physics for a while, and there's categories of items that deal with electricity. And ohms are resistance. Ohm's law we talked about a little bit earlier on in the year, where we did V equals IR, and we've actually got a slide coming up that we're mostly going to click past. But ohms are resistance. And so LEDs sort of don't follow Ohm's law because they're a semiconductor. Ohm's law applies to things that have a fixed resistance, whereas an LED sort of doesn't. It has P and N junctions that switch on or off based on the direction of the current flow, and it's more subtle than that. But you can think of them as something that turns on if the current goes in the right direction and turns off if it goes in the wrong direction. But turning on or off doesn't really follow the idea of added resistance and restricting current flow. So because they've got that weird behavior, yeah, resistance is futile is a good shirt. That might be what you're pointing at. But
That's exactly what I pointed at.
Yep. Good. Yeah, the resistor is something that will just restrict the flow of the current in a way that's predictable, and the algebra is nice and straightforward. So let's see.
I have a question.
Yeah, what's up?
So the configurations effectively are the same, even if the resistor is after the LED, right?
Yeah. Yep.
Now, does that have anything to do with the orientation of the positive and the negative of the LED? Or is it just like all things the same, you could swap their positions and there wouldn't be an effect?
So that's a really good set of questions. The LED in both cases is pointed downwards because the LED is a directional component. So because they only let current flow in one direction, in this case, current's going to flow from 5 volts down to 0 or 5 volts down to ground. And so the LED has to be pointed the correct direction in order for it to work. If it's pointed upwards, then it would not turn on. And so that's an important thing that's shown nicely in a diagram. And that means that you want to have the cathode, which is the shorter lead all the time, be the one that's attached to the ground pin.
That's
And
the negative, right?
Yeah, the negative one is attached to the ground pin, and ground is sort of like the negative side of the battery. So they're trying to help with that.
Okay.
A resistor is not directional, so there's no, like, you don't have to worry about getting the resistor pointed in the right direction. And as long as it's in series with the LED, it will restrict the current flow through the LED. So it doesn't matter whether it's above or below. As long as it's in series, you're fine. But you got to keep that in mind with the LED has to have the flow of current go from the positive to the negative. Otherwise, it won't turn on. And so that's often the case where if people are working with LEDs and they won't turn on, just try flipping it around and it might work. So that's one of the really common things. There's some other ways. So if you've plugged in an LED before and it hasn't died and it hasn't had a resistor with it, there's a couple reasons why that could happen. One, I think the box of LEDs that I bought for the group is actually a pretty robust set of LEDs. Like, they're extra hardy, so they haven't died when I've seen other ones die in the same scenario. like plugged into an Arduino without a resistor. And then a CR2032, those little batteries, the coin cell batteries that we have, they can't put out enough current to actually kill an LED. So they work really well with LEDs because you don't need resistors. They just can't, their chemistry doesn't go fast enough for them to give you the current supply to kill an LED. And if you have a really big LED, like if you have a spotlight or a high intensity flashlight, there's going to be a constant current supply so that you have the power that you need to run your LEDs with the brightness that you want. So for like stadium lighting, there's going to be different supply things than resistors, because resistors, they do waste a little bit, but they're very cheap. I bought 1,000 10K resistors this week and it cost $6. Like they're less than a penny per resistor, which is really, that you can't get cheaper than that. So this is something that's super useful. And these are for always on LEDs that are basically just connected to power and ground. If you wanted to play with this, if you have like these things sitting in front of you right now, you could plug your Arduino into a computer, plug the resistor into 5 volts and the negative side of the LED into ground, and then touch those two leads together and use the Arduino as sort of a power supply right there on your bench top. So this is a good sanity check to see if this is working. And then another thing that I really like, just for the sake of keeping it simple, is that I always use one value to partner with my LEDs. So I always use a 330 ohm resistor. And it's essentially just a mental shortcut. I don't want to have to think about it or dig through a bin of resistors to like try and find the exact right color band. I always use a 330 ohm resistor, which is an orange, brown, gold resistor. And so in almost all of your Arduino projects, you won't need to worry about it. This runs your LEDs not at their total peak brightness, but usually you don't really want them even at their total peak brightness. So 330 ohm resistors are totally fine. We'll see in a minute that you can do the math for this, and that you can try, and if you've ever bought resistors, you probably bought a multi-pack, and those come with all these color bands, and you need a color calculator like this to try and make sense of it, where you put in your colors and they populate, and then you can like see that it's a 330 ohm resistor with a gold band at the end, means it's plus or minus 5%. And so you can play around. Let's see, orange, black, red. You can do all sorts of things to try and get different colors and codes and different values to try and make sense of them. But I essentially just use 2 values ever, and one is 330 and one is 10K, the brown, black, orange that's here. So I might, if you ever ask me which one you need, I might end up referring to it as orange, brown, or brown, black, orange. But this is what I'm talking about, and I'll quickly interpret it for you. It's just my instant response. I had a license plate once that was 3,330 in my, or 33,000, yeah. And so in my head it was 3,300. It was a orange, red, which is a little nerdy, but it was the way that I remember what my license plate number was. Some of the, oh, Jamie brings up a good point. On some cheap resistors, it may not be a 4 color band, or it might be a 5 color band. Those are usually blue. There are some other versions that are out there, and some of them are poorly marked. Yeah, it's really nerdy. I get it. But the color bands are sometimes hard to see. That's another sign that you're getting probably cheaper than that's where you choose your options. I like to bulk order resistors so that I know I get a certain quality and I just have them to play with. It's not a giant investment to have 1,000 of your perfect value sitting around. So we have them, and they're on the foundation shelf. If you want some more resistors, they're in blue baggies, and feel free to take some. There's more than enough for all of us for the year. So in any case, 330 ohm resistors are what you're going to want to use. This next slide is how you would tweak that value. So here's Ohm's law applied with like more details and all the little things that you'd want to do to try and get the perfect value for your resistor. But I'm genuinely telling you, don't do it. Just for maker projects for right now, stick with 330. Don't try and tweak this value. But if you wanted absolute peak brightness, you could play around. And it turns out that if you have some interesting math to do, where you take the voltage that's supplied, you subtract away the forward voltage, and then the voltage that's left is what you use for Ohm's law. saying, I want to get 30 milliamps, the peak sustainable current out of the thing, and then you get a number that's spit out of there. So then you need a 90 ohm resistor. So putting that into context, the 330 ohm resistors run at much less than that, or because they're higher resistance, they pass less current. So, you know, we're being on the conservative end of things, but it means that you'll never have a problem. It's why I like those as a value. You could probably also be stable with a 220. But then sometimes I'm trying to decide between, is this color band orange or red? And in my mind, just keep it as simple as possible. So 330 it is. And so what do you do if you don't have a 330 ohm resistor to use? That's a really good question that probably would come up. Sometimes people buy LEDs and they've lost the resistors, or they don't know what the value is. A multimeter is a good quick way to check a value for a resistor, but you got to be unplugged from the circuit. But essentially, the short synopsis is this, that if you pass more current through the LED, you're going to get a brighter LED, which is this big graph right here. So as your forward current goes higher, so as your IF in milliamps gets higher and higher and higher to about 70 milliamps, you're going to get a brighter and brighter LED. 20 milliamps is sort of the target current that you should run for with a 5 millimeter LED, and that would be a brightness of 1. And if you went for 60, you'd be 3 times as bright. Now your eyes see logarithmically, not linearly, so it won't look 3 times as bright to you, but that's how much energy output it's going to give. And then once you pass 70, it stops the graph because it'll probably have killed itself at that point. And then also, as you get higher current passing, your forward voltage drops aren't completely fixed. They do move around, but basically any resistor you can find that's under 1,000 ohms is going to work well. If you stick a 10K resistor on an LED, it will turn on, but it will be so dim that you don't think it's on. So that's important to keep in mind. And then this last little bit, which is on the next slide, is a video of what happens if you don't attach a resistor, which is a fun experiment to try. Your Arduino probably won't do this for you, but it's totally worth it to see how this works. I'm going to play it without sound, but with subscripts like we talked about, and then I'm just going to narrate it like we figured out worked last week. So these are typical forward voltage drops. And this is Afrotech Mods on YouTube. He's running an LED here with a constant current supply. So this power supply is only capping it at 30 milliamps or 0.03 amps and at 3 volts. But if he turns this off, different and interesting things will happen. So here he's got it disconnected and it's up to 7.5 volts and there's no light on the constant current side. So he's got a fixed voltage, but he's going to let the current do whatever the current does. So he's essentially taken his brake off of the pedal, or taking his foot off the brake pedal. And so here you can see you really can blow these, right, with puffs of smoke and they get hot and then the whole thing is dead. It's passing almost 5 amps of current, which is a ton of current. And the voltage has dropped to really low because it's just draining what's coming out of this power supply as fast as it can. This is what you want to avoid. They can explode, and so you want to be careful with that. It's not always so glorious. So what he's about to do here is just a one without a resistor attached to a 9-volt battery. This is the more common failure mode that I've seen for LEDs. And so watch, because it happens fast. Boop. And that's it. There's a little bit of brown, a little bit of like charring inside, but it's super hard to see. And if you ever have one that you tried it both ways and you're not sure what happened and you have no idea why, you probably burned it out and missed it, right? That's probably the case. LEDs are also luckily very cheap. So it's good to do this once or twice just to sort of see what it looks like in the safer failure mode rather than the glorious explosion mode. But it's good to see. Yeah, these are definitely fun to make happen. They're cool to do, but I would say that that's going to be your most likely failure mode if you just can't figure out why the LED isn't working. It's either that you've got a 10K resistor in with it, or maybe you killed it and you can't tell. And if you look really closely, you can sometimes see the charring inside. So it's worth giving a close look at them. But then let's see. So here's a larger module. And so this is a large module that's designed to run at 12 volts and 100 milliamps. But the average LED, like these guys, these are set to run with a target current of 0.02 amps or 20 milliamps. So you should expect any LED that I've handed you to have that be the desired current is 20 milliamps or 0.02 amps of current. Those are the same thing, just different scales. So that's really a useful piece to know. And so if you have no idea how to get there, the core is that you just tack in a resistor. And it can be this crude if you're trying to do that. But hopefully we're going to see that it's fun to put together in a breadboard or in other formats so that you can get to it. No, don't watch the video again. Okay.
When you said it can be this crude, I think you flashed something from the video. What were you showing there?
Oh, that like it's just sort of like attached to the side of it. Like it's just sort of wrapped on there. Let me see if I can like see how this resistor is just sort of wrapped around the leg. Oh, and it immediately hops away. I want to find that frame. So by this crude, I mean like there's the resistor right there, and it's just sort of attached to the black lead, the LEDs in the red lead, and then they're just sort of wrapped around each other. So these aren't soldered. They're not connected in any meaningful sort of way. This is just like the fastest way to make sense of the fact that they're touching. So that's the sort of crude, quick attachment that you could do if you're trying to test and see is it pointed the right direction. And there's a lot of good, I've done a lot of sanity checks where like I set up where I know I have a wire and a resistor attached the right way, and then I can like quickly just touch the LED to it, not because that's what it's going to be in my target design, but just to check and make sure like, okay, am I putting this in forward or backward? Because sometimes I lose track of, I've snipped maybe the lead, so I don't know which one's longer, and the epoxy on top is opaque, so you can't see in. Having a little jig so you can check which way is forward on an LED can be really helpful. And it doesn't need to be soldered in place or even a breadboard. You can just sort of like touch it to contacts so that you can see what's going on. It's a good trick if you feel like you're losing your mind with LEDs, which can sometimes happen. I'm going to warn you in advance. They're just fiddly, and their failure modes can be so subtle, like that one that just blinked off. So that said, how do you get them to do interesting things that aren't dying and aren't just being on whenever there's power? There's lots of good opportunity to make LEDs work well. And this is where I'd love to be sitting in a room with all of you right now and be able to like attach them. But we're going to try and play around with this remotely. Oh, and then we'll pick some days this week where I'll be in so that we can play around with some resistors and LEDs in person. But there's 4 good ways that you can hook up an LED to get it to blink with an Arduino. And so these are the 4 working ways that you can get a switched LED. This one on the top left is probably the most common, although the bottom left is pretty normal also, where you've got a resistor and an LED, and these are just in line in series with each other, connected to ground. And then instead of being connected to 5 volts, they're connected to an Arduino digital output pin. So that's any one of the output pins on the digital side of the LED of the Arduino, or you can even use the analog input pins as digital outputs or digital inputs if you want. So you can attach this to any of the pins on an Arduino. You can get this to work. If you want pulse width modulation, that's only a few of them, but any of them, if you just want to blink it on and on, you can use pretty much any of the pins on the Arduino. And so on these 2, you can get them to blink normally. On this side, it's a little bit trickier, but the Arduino has all of those digital pins where it can output either 5 volts if you tell it you want it to be high, or it can output 0 if you want it to be low. And they cap out at about 40 milliamps. So the Arduino has a cap on each one of its pins, so they can only give you up to a certain amount. And we'll see that matters more later when we get to things that aren't LEDs. But it means that your LED pin, like if you put this on pin 8 on an Arduino, let's say, pin 8 is attached here. And when you write pin 8 to be high, then it will be at 5 volts and current will pass down through here and it will go back into ground. And so when you write it high, it will be on, and when you write it low, it would be off. Because then down here would be at 0, and the top, if it's written low, that would be at 0 also. So there's no voltage difference, and it won't turn on. The same is true here. It's basically the same thing. It's just that the resistor and the LED are switched. This one is a little bit trickier, but it's essentially the same thing. And for those tester boards that I've designed and given to many of you already, this is the setup for the RGB LED, where they're a common anode. And so in this case, or maybe it's this one specifically, but in this case, your LED is attached to 5 volts. And what you're switching is not power. You're switching, is it connected to ground or is it connected back to power? Because if you connect it to ground, then the charges want to move down through and exit because that's its connection to ground. And that's called sinking current. And the pins can source or sink up to 40 milliamps. So that's totally fine. But then,
Right.
yeah.
I'm a little confused. Can you give examples of each of these? So I mean, I can understand the diagrams, but for whatever reason, my brain's just not like understanding what you're talking about here.
No, you're totally good.
Yeah.
Let me see if I can do, okay. So the real key that you need to have for an LED to be turned on is it needs to have voltage across it, right? And so an Arduino runs at 5 volts, and there's 2 ways to get 5 volts across the LED and resistor. There's the normal way, which is the one over here on the left, where you write it high, and then you've got 5 volts up here and 0 at the bottom, and then there's a 5 volt difference across it.
Yeah.
Right?
Yeah.
And so the difference would be 5 minus 0. So that, that's sort of a interesting and trivial elementary school math problem. 5 minus 0 is 5. So we're all good and happy. What's weird about it is that over here on the right, in order to get 5 and 0, I do that by pulling this low. And so I have 5 minus 0. If I write this high, which is normally what on would be, that means that the top of the resistor LED pair is at 5 and the bottom is at 5. So 5 minus 5 is 0. So there's not a voltage difference if I write this to be high. It's sort of like, instead of connecting this to the bottom, I connected it back to the top, which is weird. And there's not, most of the time in my brain, I always hook them up like the one on the left. I think it just makes more sense. And if I were to give you any recommendations about how to do it, I'd say do it like the ones on the left, where if it's high, it's on, and if it's low, it's off. But you can do it with inverted logic. And from time to time, that is useful, or the situation that you're sort of backed into. And so they're interesting to see that they both work, but they're definitely a little bit tricky. It's kind of fun to make both of them happen. And so it's worth it to, absolutely everybody should get the one on the left working this week. But if you want to try and challenge yourself, go for this one on the right also. It's definitely weird. It will still work. If you hook it up this way electrically, it will still work with LED blink, or with the example sketch blink from Arduino, but it works exactly the opposite way. When it's written high, it's off, and when it's written low, it's on. And that's totally weird. And if you're interested in going deeper on that, we can totally do that. But it has to do with the fact that it really requires a voltage difference to power rather than just a voltage applied. So
Corey, sorry.
Yeah.
Could you give an example? Is there a project that you think would make more sense using the inverted logic versus the standard?
Not necessarily. It's something that, like, if you're buying, sometimes it's helpful if you happen to have common anode LEDs or common anode RGB LEDs. So like usually it's because of an economy thing, like it's cheaper to buy the part that would have you do inverted logic, or because you want to. It's tricky to wrap your head around at first, but then when you get more experienced as a coder, you realize like it's the same exact thing. You just flip a 0 for a 1 and it works the exact same.
Okay.
It's not I would say there's no reason to make this your goal if you're designing a circuit. Every time I design a circuit, I always do it with the things on the left, but sometimes you have to deal with it on the right. And I just wanted you to all see that this is a way that you can deal with it.
Wait, if the cathode is on ground, or I'm sorry, if the cathode is at the Arduino output, or how is that working exactly?
Yeah, I've got, let's see, boom, it's coming. It's here. So sometimes you buy common cathode LEDs where they all come together at ground, and sometimes you buy common anode where they all come together at power. And so it depends on which one of the two versions of RGB LEDs you bought.
Okay,
And
so it's not across the board, and it
yeah,
has
it's not
nothing to do
across
with,
the board.
and it's
It
not
just
like a
has,
pull-up resistor. This is different.
yeah, it's just sort of different.
Okay.
It's
Okay.
a quirky thing that you probably won't need, but it's good to know that it exists in case you happen across it at some point. So these are switched LEDs. Stick to the ones on the left. If the ones in the middle or on the right side, I guess, if they feel confusing, you can successfully avoid them for a long, long time. So you don't have to worry about it.
So it's very specific to the LED you get.
And how you have it attached, and like the drivers, like if you wanted to use, if you only had access to, if you have certain types of transistors prefer certain types, if you're using a transistor to drive them. So there's different contexts where you may need to use one or the other. Like an N-type transistor might like the right-hand version a little bit better.
So is that still a true diode where with that LED it's flowing from the cathode
Mm-hmm. Yep,
to
it's
the
flowing. It totally
or
is. It's just a power trick, but it's totally a diode working in the right direction. And so this is something where I would need, what I really want to do is find, let's see, print screen, and then, oops, see if I can pull up Paint and paste that in. Okay, so in here, you're really getting your current to flow. If you've got one of these, it's like the current comes down this way, but instead of being attached back through, let's go with a bigger, more. Yeah.
your scientific calculators up. I'm not
Oh
sure.
yeah, we'll get rid of that thing. That's,
I wasn't sure if that was.
yeah, no, that's just on accident, but it's not in our way directly. So
Okay.
here it goes down, and at this point it can either go down into ground, like that would be the normal way if it wasn't switched. But basically, this I can either have be attached to 5 volts or to, so if I have this at 5 volts, it's like it's attached back to here, and there's no path to ground for it to go to. So this is what happens if I have it written to high. It's just sort of looped back around to 5 volts, and then there's no voltage difference that makes it have any reason for current to flow through the diode. But if I go the other way and attach it to low, then it's got a path where it can go through and it can make it all the way to ground. So it gives it an opportunity to pass current all the way through if you write it low, which is definitely goofy. It for sure is.
I have a
So if
question.
you write it high, it's short circuited, basically.
Writing high, it's not got a voltage difference. Yeah. Yeah. The question. What's up, Aaron?
So okay, so if you don't let it ground,
Mm-hmm.
the ground like functionally isn't functional. Like it's not playing a role in the circuit at all.
Yeah, it's not playing a role. I just put the line there to see that it kind of isn't involved.
Right. So like if you were creating a system where a ground was needed, maybe like
Yeah, an Arduino
yeah.
always has the ground pin.
Uh-huh.
This is just saying that you wouldn't need to attach to it.
Interesting. Okay.
Yeah, because you're using the digital input pin or the digital output pin as the ground when you switch it to low. And when you switch it to high, it's serving as another 5 volt pin. This is an interesting one. I'm going to make a video of like playing around with this and showing how this works. But I don't want you to get, this could be a forest for the trees moment. And let's stick to the one on the left, if that makes sense. And you're trying to make sense of how to do these things.
Sure.
Do the one on the left for sure. So, how about if you want more than one LED in a project, which is often the case. If you want to have a fun Blinky project, you want to make sure that you're thinking about how do you attach them all and how do you get it to work. My recommendation is that each one gets its own IO pin and each one gets its own resistor. So you want to make sure that they're individually controlled. And it's for a few reasons. But one of them is that this lets you have finite control about each one, and it also manages the power, so it's not all bunched up onto one thing. But you can't put them in parallel, your LEDs, because each one takes like 2 volts to use, and it won't really work right if you have 2 in a row on an Arduino, because they only give you 5 volts. So it's not quite enough to turn on both of them and have it glow nice and bright. So you don't want to put them in series, and if they're in parallel, then only the LED with the lowest forward voltage drop will turn on. And that's, we can get into series and parallel about why, but that's another one that I just want to discourage you from doing. And it's a longer discussion to go into the why for that one. It's a worthwhile discussion, but if you're just trying to get things to turn on, it may not be the discussion to have this moment. There are some interesting solutions for how to have a whole bunch of LEDs. Those are shift registers, addressable LEDs, and Charlie plexing. And those are coming up a little bit later on. Interestingly, there are moments where putting LEDs in series are the right choice. Like the lights behind me on the tree, those are LEDs and they're definitely in series. They blink at 60 Hertz because they only let alternating current pass when it's going in the one direction. So they actually are blinking super fast. You just can't tell. Unless you're like crunching on hard candy and looking at the tree, then you can see them sort of blink as your persistence of vision is broken. But that's its own whole other thing. In any case, I made this maybe less than quick note sheet so that if you're trying to make sense of an LED circuit, you can look at this and try and make some reference points for, is it connected correctly? Like, do I have the resistor that I need? Do I have a connection that I want to have? And did I accidentally hook it up in a way that I didn't want to have it? Like, those are all important things that hopefully this note sheet will help you sort of determine. And it's got all a fair amount of notes on there that hopefully, fingers crossed, will help you get it right, or check to see how you got it wrong so that you can correct it. So this is something that you can come and take a look at. But basically, this is going to work even if we have RGB LEDs, because RGB LEDs are basically the same thing, just a triple package. So let's see. The next big thing that I want to talk about is pulse width modulation. And so this is a really helpful feature that you can use with LEDs because it blinks them on and off. LEDs are fundamentally a binary thing. They're either on or they're off, and that's not strictly true, but basically it's easiest to think about them as only having 2 states, on or off, and that's it. And so if you want to get an in-between or like a half brightness LED, you really have to get tricky. And so pulse width modulation is the way that we can be tricky. And it's the analog write function of Arduino. And so what it does is it turns the LED on for a short period of time, and then it turns it off for a short period of time. You can decide sort of the ratio. And so if you want an LED to be totally off, you'd analog write in 0. So it's on for like 0% of the time, or more accurately, 0/255 of the time. And if you want it to be 25% bright, you put in a 64 and it's on for 64/255. Each one of these like little green sections is a regular cycle. Pulse width modulation on an Arduino blinks on and off, I think 495 times a second. And you're just using analog write to decide how much of that time is it turned on. It's a good way to get brightness on LEDs, to do color mixing, or we'll see with motors that it's a good way to set motor speeds. So pulse width modulation is a really nice feature that's just built into Arduino, where you can use analog write to get faded brightnesses. And it's a great trick. If you've done the example sketch for digital fade or for analog fade, I think it's actually a basics fade, that should work well for getting to play with this. Voltage control brightness is a little trickier. So it depends on what exactly you mean for voltage control brightness, but pulse width modulation is simulating having different voltages. So if you're, is one way that it's often described. I don't actually love that description for pulse width modulation. But if another way to think about this is that if I put a 50% duty cycle, which means half the time it's on, half the time it's off, for this 5-volt level, it's kind of like I'm giving it 2.5 volts. So it's kind of like I'm half powering it. I don't love that because it it muddles the forward voltage part of an LED. But it is an interesting point to say that it's sort of like simulating an output voltage that isn't 5, which is useful. But this is mostly going to be useful for us if you want to just fade an LED, or if you want to blend colors in an RGB. So it turns out, Jamie, your question is, can you just lower the output to the pin instead of turn it on or off? And they're digital pins, so you can't. Some microcontrollers can, and Arduino articles sometimes are unclear. They say that analog write is analog writing a lower voltage, but you're really blinking it on and on faster than you can see, which is an important trick that gets used in all sorts of different levels. There are some microcontrollers that do actually change the voltage level. But then if you ever tried to use a 25% duty cycle and it was really 25% the 5 volts, you wouldn't be above the forward voltage of the LED and it wouldn't turn on. So it has to go between full on and full off in order for this to work. And it's just playing with time and your sense of persistence of vision in order to get reduced brightnesses, which is actually, I think, really cool. But it's definitely a subtle art for how this works. And it's a lot of technical, but when you go to analog write some number that's lower than 255, you'll just see like, oh, it's brightness, and it just works, which is actually great. So let's say you want to get an LED to show as on or off, and you want it to persist in that state. You need to have time for it to show that it's in that state. And this is why in the basics example for blink, there's a delay function where it's by default, it's delay 1,000, which is a second. But you need more than about 30 milliseconds because that's how much time it takes for your eye to register a picture. 33 maybe. For like old cartoons, there's 30 frames a second, right? And so a 30th of a second is about as long as you need in order to see something. And faster than that, faster time frames, and it starts to blend together. If you want to play with that, you can use the analog in out serial example sketch in Arduino to sort of play around with that to see how fast is your persistence of vision. It's a good early test with Arduino. In pulse width modulation, this is done for you. Like all of the time part is managed for brightness and time on or off. But if you're digitally writing, you have to manage this by including delay or some blink without delay function, which is another good example to look at. But if all of that is taken aside, all of that's figured out, next up we have RGB LEDs, which are red, green, blue LEDs. And so these are interesting triple pairs. So here in the top left, I've just got 3 LEDs put together, a red, a green, and a blue. But you can get these super small. So this is like a microscope view of the die of an LED with the red, the green, and the blue all on there. And you can see the sort of whisker connectors that are inside of LEDs all the time. But normally you just don't look that closely at them, although you should totally look at one closely if you can. But in there, there's 3 LEDs in one package. And usually these have 4 pins as an output. They're shared pin, which is maybe an anode or a cathode, and then the 3 pins that are individual control for the 3 colors. And so these give you red, green, and blue, where you can turn those on and off. And if you crossfade them, right, here's a red, a green, and a blue. If you crossfade them, you can get pretty much every color of the rainbow, which is really great. So you get all of these Rgb Biv colors with the secondary cyan, magenta, yellow, and all the things in between. So you can get all of the colors that you would get on a computer monitor. There's a few interesting things like brown isn't on there because brown is only a contextually seen color where it's like a darker orange. Some other interesting stuff. Black is when it's off. So black isn't in this color wheel either. That's when all 3 would be off. If you have an array and you just need some context to see that also. But it's interesting. Another thing that's a little tricky about RGB LEDs is if you're trying to go for perfect white light, usually it's a little bit bluish if you just turn all 3 on, because the blue LEDs have a higher forward voltage drop. So it's not usually super easy to get a perfectly tuned, like a nice central white. And so I've actually bought LEDs in the past that have 4 dyes on them, a red, a green, a blue, and a dedicated white chip, because it saves some power to only have one on instead of three. And that dedicated white chip can be tuned to just the right pitch of white. If you're thinking about how many Kelvin it is for a warm white or like a cool white light, that's something that's a little bit tricky. You can dial it in with RGB. You just have to put in some effort, and it changes a bit chip to chip sometimes, like category or batch of chip to chip. But how do you, these are all just things about the LEDs themselves and sort of how to hook them up. How do you do stuff with them? And so when you're looking at LEDs and how you want to animate with them, there's some simple animations that you can do. And when you're thinking about animating things, it's often really helpful to think about that happening with frames. It's not the only way to do animations, but it's a nice, straightforward one, is that when you think about frames of animations, you're going to have different things that you want your LEDs to be doing in different frames. So over here, we've got like frames and a little animated character, I think probably flossing. But over here on the right, this is a two-dimensional array where it's an array of arrays. So each one of the rows represents one frame, and each one of the columns is what one particular LED is doing. And it would definitely take some time to unpack what's going on here. Ruby's working on this. This is a fun project that Ruby's going after. And so this is some example code from her. But in here, you can say what you want each pin to be doing, what you want each LED to be doing, and then updates every frame. And these frames last for 1/10 of a second. So these are a little bit slower than persistence of vision frames, but it's still, you can decide what each one's going to do as you go. This is maybe the simplest way to do animations. We'll see some more elegant kinds of solutions in a little bit. But thinking about animations frame by frame can be really helpful. The rest of this is just like hammering through this array and turning it into the LEDs turning on and off. So how would you manage a lot of LEDs? The example we just saw was for 4, but if you want a lot of them, you can do, essentially there's 3 good tricks. There's matrices or Charlie plexing LEDs where they're connected in interesting ways that are sort of like combos of those 2 ways you could hook them up. And if you do those combos just right, you can actually control a lot of LEDs with a much smaller number of pins. So if you can balance those 2 configurations just right, you can get, I think the example we're going to see in a second is that I controlled 6 LEDs with just 3 pins. So if you play with time and connections just right, you can optimize how many LEDs you drive with a smaller number of pins. And then another one that's really easy, relatively easy, is Adafruit's Neopixels. These are addressable LEDs, and addressable LEDs has become an entire category. These take digital information and they have a little controller chip inside the LED itself. So you're sending commands chip to chip to chip, LED to LED, and you can write animations that way. Adafruit has really turned this into a solved problem. It's super nice and easy, but you don't even have to use their branded things. They just use 50/50 SMD chips. And if you use those, you can design these yourself without buying their product. Their products are great though. And then the last one is shift registers. And these are sort of an older solution for this, but they're really great. You can use them as other integrated circuits you add in, and they let you sort of multiply your connections coming out of the Arduino. It takes 3 pins from the Arduino, and you can use a shift register integrated circuit, which is just another chip that looks like the ATmega, and that will output to 8 more things. There's some 74HC595s, which is the name of these terribly named chips. I found a few of them in MakeHaven yesterday, and so I stuffed them under the TV screen or the monitor that's attached to the microscope in the electronics area. So if you want to see what those look like or play around with them, there are a few that are in there, and they're just like stuffed underneath that monitor. So you can play with those. Now, how do you do more complicated LED animations is an interesting question. And there's lots of good solutions, it turns out. Adafruit, for those addressable LEDs, they have an Uber guide. This is a really robust guide on how to use these addressable LEDs to get really fun and really complicated animations pretty easily. They do that with some really well-written Arduino code that you can play around with. But there's tons of other people who've gotten really passionate about, there's the idea of an LED cube. Charlie plexing in 3D gives you these fun cubes of LEDs, and you might have seen those, but people really love the cleverness of the code you have to write to solve that. And so there's several, these are 5 linked things that help you solve that problem. And so those are
Question.
all interesting pieces. Ooh, that's a good question. So Ada, for how do you solve the problem of forward voltage drop for a lot of LEDs is a totally good question. It turns out you still power each one separately with their own little circuit, and you deliver power along. So each LED has its own link directly from the power line to the ground line. And then in like the Neopixels, they're each attached to power and ground, and then there's a data pin running along them. In the case of these LED cubes, you have arrays and they're blinking on and off in really weird fashions so that you can cleverly solve that problem. And it's definitely something that you're gonna have to do some, I can help you with it. I can explain it at length. I just want you to see right now that it's totally a thing that you can solve. If you wanted to build an LED cube as sort of your project for this week and next week, it's completely a good way to go. It's totally a fun project to do, and it integrates a lot of interesting skills and is a good code project. And then there's great support for that. There's a big community of people who build LED cubes, and they look like lots of fun, or they are lots of fun. So you can totally play around with these if you want. And here's 5 animation things. And then you can also custom write tools. There's some really fantastic LED displays that you've seen around the world. Asia loves to light up their buildings in LEDs all the time. And those are going to have custom written solutions where they're individually addressing and controlling those LEDs on the sides of buildings. So those are definitely interesting pieces. And the control code for that is something that would be fun to dive into if somebody really got into it for a giant LED display. But the last thing that I wanted to make sure that we got into, and we're sort of like cruising in for time, is how do you take an idea like this and go from the process of I have a thought to I have a thing that's made. And so I want to talk quickly about the general progression of how do you go from idea to built thing. And so I think about it in these 5 stages, which is a lot to decode all in one shot. So I'm going to leave this up and we're just going to sort of work our way through these 5 things. On the left is the diagram. And for me, a circuit diagram is like a plan for how you're going to build it. It's very much a blueprint where you're thinking about the connections that you have. It may not be exactly how you lay things out in physical reality, like where they're located next to each other, but it's going to point out the connections that you want to have. And so I've got this one that was animated earlier, and then a bigger one. This is for like a radio down here. But circuit diagrams like that help you diagnose the logic of what you're doing. And they can be really helpful for showing this needs to be connected to that, and this needs to connect to there, without being like where you plug it into the breadboard. If you have a diagram or an idea of a circuit, the next place that I usually build it on this progression is in a breadboard. So a breadboard in my mind is the next step towards more permanent solutions, where you use a breadboard because they've got little clips inside that will grab onto wires or grab onto components, and you can easily pick them up and move them around. You don't have to solder anything. They're good for testing. They're low commitment, and they are to some extent expendable. So a breadboard can be $3 to $20 depending on the quality and size that you get. But these won't last you forever either. You can definitely get into trouble if you think your breadboard is perfect for 5 years. So you got to be careful about it. They often will not even last a whole year if you use it aggressively. So you got to be, and sorry, Jamie, I see that little nod. It's definitely painful if you realize that that's the problem that you've been having. But a breadboard, you got to be a little careful for. They're a great way to test things though, for sure. The next progression is a perf board, and I've had lots of projects that stop at this point. But a perf board is a place where you'd solder together your components. And so here it just looks like a board with a lot of holes. On the underside, they often have copper in traces or in connections that connect several of those holes together, or sometimes they're just a little copper loop around each hole. But they give you a place to put in your connection, your elements or wires, and then solder them into place so that they're more permanent than a breadboard would be. A perf board is a great place for maker projects to live, especially when you're just getting started. They're usually simplified circuits. They're relatively nice. Adafruit sells Proto Shields that have perf board on them so that you can put them on top of your Arduino and then solder on the components that you want to have to make a nice simple circuit. I used to buy those by the gross, actually. And so getting a Proto Shield for an Arduino is totally a good way to go if you just want to build a relatively simple thing that sits on top. This is a good way to make it happen. The next thing in the progression is a milled PCB. And so if you have some CNC skills and CNC tools, you can totally design circuits in software. And we're going to talk about circuit design software in a few weeks. But you can design circuits in software and then use a CNC to cut them out of a piece of copper lined board so that you have a circuit. And so this one that's blinking is actually the one that's the front page of the Foundation's website. And so let me actually go to that. Oops, let's get out of here and we'll go to the, we're going to search for Foundations of Fabrication. Oh yeah. Good question. So the shift register, so two questions popped up. The shift register is good for managing all of the power for you. So you don't have to worry about all those details. The chip is Foundations of Fabrication. The chip actually does a lot of the work for you in managing the power. It just sends out the control signal. So it's basically like multiplying the capacity of your Arduino by just duplicating pins, sort of. You send it commands over SPI and then it reuses those commands on the pins that it has by dealing with each byte that it gets bit by bit. So it's a shift register. It's an interesting little chip, and you can actually read the annoyingly long data sheet for all of the logistics, but it manages the power and the code, the logic for you all in one shot. So they're helpful little chips. Protoshields, let me pull those up also. They are Protoshields for Arduino, look like this. This is one for an Arduino Mega. And so here it is. It's just got all the pins and things that would fit right onto an Arduino, but then it's got solder perf board sort of connections right here. So if you wanted to play around with soldering right there on top of the Arduino, it keeps you in sort of a small form factor. And they're really helpful for if you want to have a nice compacted thing that you know is going to just need a couple connections to Arduino pins. So it's totally a good option if you're trying to do that. But this is the milled circuit board that's really small on the slide that we're looking at. That's actually the front of our whole website. This is a little AT-Tiny 424, I think the same kind that Wagata is playing with. And so this only has 6 output pins, and some of them were being used for other things, but it's using 3 of them and 3 resistors to drive 6 LEDs. So this is a Charlie-plex set of LEDs being driven by a very small chip. And so this was just a way for me to sort of push the edges of building circuits, and then also how can I control more LEDs than you'd think you can. And so this is an interesting thing to go into. It was definitely part of my Fab Academy journey. And if you want the whole design for this and the code, it's all available, and I can send you some links to that. But it's totally an interesting way to go. This, I would say, milled PCBs is a really cool skill. And it's fun to do if you have especially surface mount components, although the LEDs are on the other side, they are through hole on this particular thing. But usually this is something that I do if I was trying to work my head around an idea and a design before I order a board. And increasingly, this is getting cheaper and cheaper to order PCBs. Like the ones that are here, I got for $2 is a promotional price from this particular manufacturer, JLC PCB. But for $2 for your first order ever, they'll make you your boards that you've designed and ship them to you with free shipping from Shenzhen, China. And so you submit a design to them as a series of files, as Gerber files, and then they'll send them back to you as perfectly made boards. You can even pay an upcharge and have them solder components on for you if you choose from their library and you're willing to pay the extra fee. But it's a nice way to get completely professionally made boards exactly to your design if you're super interested in it. Milling circuit boards is something I've looked into at MakeHaven. With the Shipoko, it's not possible. I tried it. It doesn't go out well. I've tried laser cutting them. It's something that's on the horizon for something I want to solve. I might need to use the Tormach. And so then I need to convince JR that I should be able to use that CNC with all of you. Or I think the Gerber can handle it, but I would need to try it first. But there's an entire tool chain where you need a new software, and then you use FlatCam to get the tooling ready. But it may be something that we can do at MakeHaven, and I would love it if that was true. If nothing else, what we might be able to do is make one of our projects when we get to machine building is to take an old 3D printer and retrofit it with a end mill so that we can build our own like specifically circuit board sized milling machine just for milling circuit boards at MakeHaven. So I'm totally interested in, by the time we get to July, milling circuit boards at MakeHaven. It's just how much struggle do we need to go through to get there. So we'll be doing it by the time we finish the class, but it may take a minute. So this is something that we can totally work on, but this, just knowing that this progression exists and sort of how I would relate these 5 steps together is something that's relatively useful to see that sort of where you're going. If you never make it, like if your Arduino projects live in the perf board space, you're totally good. I would caution you against stopping a project in a breadboard place, because the connections do get weaker over time and your project will fall apart. You definitely want to transition to perf board if you want to keep it around for more than a couple of days, because the breadboards do just wear out. So you want to make sure that you get to this point. And so that means that we're going to be soldering very soon. It's absolutely in the slides for next week, but I've got some videos that you can watch on the website as well. So what's next? Here are the things that I think would be useful to try for LEDs this week if you didn't want to just full on jump into an Arduino project, which is sort of where we're going next week. And so these are the ways that I'd say you should get started. First off, you just want to light an LED with a 330 ohm resistor, like just power to ground LED in the middle. Make sure that you've got the sanity check for that. Next up, use an LED in a breadboard. Get it to blink, get it to fade, do all those sorts of things with the LED into the resistor. Make sure that you've got those things, and those have got example sketches for you to use. Then try and control multiple LEDs, and there's some example sketches for that. But you could write your own code, or you can use the examples. You can sort of explore, what does it look like to have multiple LEDs that are in play? And then what does it look like to have an RGB LED working? We're going to have both types of RGB LED by tomorrow. There's already common cathode RGB LEDs in MakeHaven on the shelf in the blue box. So if you wanted to grab one or two, a handful of those, you can. I have 100. But if you want the other type that you'd solder into the board that I gave people, you can do that as well. And then you can try Charlie plexing if you're interested in that, which is sort of the step towards a LED cube. Or if you wanted to get super crazy, you can measure forward voltage drops of LEDs and observe some of the properties that are described by data sheets, just to go nuts with that. But if you wanted to, this is just sort of a sanity check that you totally make sure that you understand what's happening with LEDs. Basically, for the course requirement, just that you can get an LED to work reliably and that you know what's going on with it. That's really the goal. If you wanted to see where we're headed next week, we're going to be headed towards, let's see if I can pull it up here, units and intro electronics. We're headed toward, and here's some great videos to watch, like how to use a multimeter, resistance voltage, that sort of stuff. This is where we're headed next week, which is just projects. We're going to talk about the Raspberry Pi versus Arduino, sort of what's similar and different. This is a list of projects that I have found and I've looked at them. I haven't done all of them, but there are instructions, pictures, code, those sorts of things so that you can build projects that you might be interested in. And so that includes like this time triangle. That would be a good one to add to the list, although I haven't done it. Basically, any instructions you get on Adafruit are super good. They're really nice. I would 100% recommend any Adafruit LED project. And then Instructables is another great resource for projects. Like this is a binary clock where you get LEDs to blink on and off. And it's showing you in binary the time, which is a very nerdy way to have the time. I can't right now inherently read this, but you can get used to it, I'm sure. And then there's a conversion factor where it's just a series of LEDs. And I think in here somewhere, the guy the person who made it shows sort of the background. When you're deciding on an Arduino project, you want to get something that has a bill of materials, that has like, here's the prototype and some pictures of what's going on, that they have designs for what they made. A circuit diagram is really helpful to have something like this to go from. This is pretty common in Instructables or in maker spaces, or in sort of the maker sphere where they use Frixing for your circuit board design. This is absolutely going to be helpful if you're trying to make sense of what's going on here. And so this is a mini Pro Arduino. So this is just another flavor of Arduino that's small. And then how they connected all their LEDs. You can see it looks like they're using some of these as outputs and then some of them as ground. And it looks like this is probably a Charlie Plex set, just based on the way that they're attached. That's pretty common for how a diagram would look for Charlie Plexing. So there's lots of interesting things to try and look at and make sense of. What we're going to do next week is try and just hop in and make one of these projects work. And it's totally the right move if you think that's going to take me 2 weeks, pick something that has LEDs in it as your project and go for it. Good examples would be like the Arduino binary clock, the word clock. I really love these, where it's got words here and they're sort of backlit by LEDs. So they come out looking really cool. That's a fun look if you wanted to do that. And it's totally an Arduino Uno project. So there's a fair amount of wiring, and these are all shift registers. So those are all interesting pieces to use. Oh, and there's a milled circuit board. But you want to sort of gauge where you're at and where you want to go for how complicated you want to get. My guess is that if you dug around on Adafruit, there's probably a word clock board that's pre-made. And for these starter projects, there's no shame in ordering yourself a pre-made board that says, I want to learn the logistics of attaching these things together more than you want to worry about the circuits of all that. So if you find a project that you're passionate about, and Adafruit has, let's see if we can do Adafruit word clock, you can hop in Neomatrix. Look at that. Boom. Neomatrix 8x8 word clock. Here's this. Here's your parts list. And there's all of your stuff. So these are often a little bit more expensive, right? Because they're very buttoned up, but it's a really good set of instructions to follow. This is absolutely a good way to get started with projects and to make sure that you feel successful at the end of the week, which is sometimes the most valuable part of it. So take all of those things into account as you're looking at where you want to go over the next week or so. Oh, this is a fun one too. 3D printed animated flying toaster OLED jewelry. That looks like fun. There's tons of cool things that you can do. I want you to explore any and all of them that you are interested in that relate to LEDs, but make sure that you know at the end of the week how to get an LED hooked up and how to get it going. So that's really the goal. But I've definitely talked longer than I should have. So I want to hear what you've all been up to on the laser and the vinyl cutter, how things are going. And I'm going to stop sharing my screen so that we can have more of a conversation.
Just one more question. The
Yeah.
schematics that you made up, how did you draw that up? What like tool did you use?
I used Eagle because I'm an Eagle native, but I'm trying to convert to KiCad, which is an open source version. JR likes to stick to open source platforms as much as he possibly can. And so I'm trying to make the conversion over to KiCad, which is completely open source.